Environmental monitoring refers to the systematic process of measuring and controlling the cleanliness and environmental conditions within a clean room to ensure it meets required standards. This is critical in industries like pharmaceuticals, biotechnology, semiconductor manufacturing, and consumer goods, where even tiny particles or microbes can compromise product quality and safety. To learn more, I'll turn it over to John Saul, JMP founder and chair. John?
JMP 19 with process screening is very good at analyzing data from environmental monitoring. Every pharmaceutical manufacturer needs to monitor its factories for possible contaminants from the environment. Mold and bacteria are two of the threats that can ruin a batch. And other kinds of factories, like in the semiconductor industry, are threatened by airborne particulates. These facilities have specialized collection devices for environmental monitoring, and each monitoring device reports many times a day, and there are usually many different devices across each facility. It becomes a challenge to process all this data in a meaningful way. Now, the process screening platform in JMP is used to monitor many processes to determine if they are in control, within control limits, capable, within spec limits, and stable, not shifting or drifting. It can sort the processes by various measures, chart them, and provide various summary graphs. Now, previously, process screening only handled normally distributed process and monitored whether a process was near its target. But in JMP 19, it will handle non-normal processes, especially processes that you would like to keep from becoming large. Count processes, such as contamination counts, non-negative continuous processes, such as contamination rates, and proportion processes, such as defective rates in batches. Now, phase 1 in monitoring is for evaluating the distribution of each process to propose control limits. Now, traditional C-charts for counts assume a Poisson distribution, but often Poisson does not fit well, and so we fit several distributions. Poisson, where the mean is equal to the variance, negative binomial, where the mean doesn't have to equal the variance, the zero-inflated Poisson, and the zero-inflated negative binomial. And it picks the best fitting, the one with the lowest AICC. So once we have estimates of the distribution, we want to determine action limits and alert limits using the quantiles of the fitted distribution. The action limits is typically chosen at the 0.9985 quantile, like normal 3 sigma. And the alert limit, kind of a warning, is chosen at the 0.975, like the normal 2 sigma. These are the terms used in environmental monitoring instead of control limits and warning limits. Now, once you have phase 1 done and you have control limits, phase 2 reveals which processes go out of control and when. We need to provide summaries of the processes, sorted to bring forward the processes that most deserve your attention, the ones with the high alarm rates, and show an alarm graph at the time of each alarm, and create control charts of the processes of interest. So let's see how that works. Here's some simulated environmental data from many different devices. And let's take the grouping variables that identify each device and their grouping variables. And the count is the process variable, and the time is the time variable, and the control chart type is count. And once we run that, we now see the summary, and it shows each of the processes sorted by the alarm rate. Let's make room for some other things. And let's invoke an option called Show Charts as Selected. And so each time I select a chart, it will show the control chart for that. And here you see the ones that had action alarms. Here's the first one, the second one, the third one, the fourth one. The fourth one, as you see, the best distribution was a zero-inflated negative binomial. And you see lots of zeros in the process itself, explaining why it chose the zero-inflated version. And then you see the upper quantile limits labeled on the chart, as well as in the summary. Once we have this, you'd like to see where all the alarms were in time in one meaningful chart. And so we have the alarm graph to do that. And so for each process that had alarms, we can then see where that alarm was in time, and we can hover over that to get a short version of that chart, a small version of that chart, and we can even select a bunch of charts that seem to occur at the same time, perhaps indicating cross-contamination across various locations. Let's look at a limits table. Once we have the limits set, we can store those limits in a table, and once we bring up using that limits table, it calculates a few additional things like capability index. In this case, it's seeing lots of alarms for one processes because we set the limits very different from the quantile estimates. Okay, so now let's take a look at how it's published in JMP Live. Here we have the original chart, and I published this yesterday in JMP Live, and it's now loading it, and you see the same kind of summary graph sorted by the alarm rates and the alarm graph, and I can then now select on those alarm graphs to see what the characteristics of those processes are. Okay, so it's interactive just as it was in the desktop. Now, in addition to count processes, we also support non-negative continuous data. And for these, the distributions fit are the exponential, the gamma, the Weibull, the log normal, and the zero inflated versions of each. And we also handle proportion data, p-charts for defect proportions. So there you have process screening, not just for normally distributed processes anymore.